So in the previous video, we learned that the propensity score is a new variable that is sufficient for our analysis. We don't need to match all the information in X, but we only need the propensity score information. That's the idea, and the propensity score is defined as the probability of treatment given observations, right? And then the theorem here, this is the theorem summarizing what I said so far. So if the potential outcomes and the treatment decision are independent, conditional on X, so this is the conditional independence assumption. So if the conditional independence assumption holds, then the potential outcomes and the treatment are also independent, conditional only on the propensity score, right? So under the same conditional independence assumption, simply you can utilize the propensity score. That's the mathematical theorem, and the textbook proves it. If you're interested, you can try to understand that. But I explained the main intuition, which is, I believe, clear. So then, as before, we are going to repeat kind of the similar process we learned, like from the matching estimator. What we how we study the matching estimator can apply to the propensity score matching estimator. So propensity score matching estimator can be denoted as delta as a function of p. So the propensity score is a probability, so p can run from 0 to 100%. So the propensity score is between 0 to 100%. So depending on the propensity score you are interested in, you can think of the average treatment effect for a specific, that is specific to a certain probability, right? So for example, you can calculate the average treatment effect for those who are likely to take the treatment with 50% or 70% or 90%. So that is all possible. And okay, so if you calculate this, and this is what you can calculate, and then by the theorem, this estimator equals the propensity specific average treatment effect. So this is average treatment effect, expected treatment effect, conditional on certain propensity score. Okay, so there are some comments on this estimator. First, the biggest advantage of this estimator is that you only need one dimension. One-dimensional matching is a big advantage because computationally it's possible, tractable. So that's the reason why we studied this. And however, this also comes with some additional problems. First thing we have to worry about is, think about this. I said this is the probability of taking the treatment. How do you observe that? In your data, you only observe whether a person attend college or not the probability. Probability is kind of hidden. It's another hidden variable. Then how can we utilize this? That is estimated separately. So we have to estimate the probability of attending college first. In the first step, estimate this, and then you can implement this method. So it's an additional estimation burden, and the textbook discusses a lot about its estimation problem. There is many theoretical challenges and like many kind of arguments why it's not a problem, but I will skip that. That's more technical and theoretical discussion. But simply the conclusion is that it does not matter. So in most cases, estimating the propensity score is not that challenging. It's not a big problem in practice. So we know how to estimate this. We know tools, statistical tools to estimate this, and we can theoretically prove that this estimation does not affect the statistical error, standard error of our final propensity score matching estimator. So, simply speaking, you don't need to worry about that. So this is a potential problem, but not a big problem. So the first problem turns out to be not a big problem. So I will show you two more problems which need a little more discussion. So let me show you. The second problem is interpretability. Okay, so x is real substantial variable like family income, high school test score. So these are kind of tangible. You know what they mean. But propensity score is purely theoretical variable. It does not have, like, okay, you can say that that's the probability of attending college. But there is no substance. It's a theoretical, conceptual variable you never observe, and it's rarely relevant in practice. So, for example, there is no policy. If you design a policy, it cannot use the propensity score as a reference. Like if you develop like fellowship program, but the fellowship program would be based on the family income, not based on propensity score. So in that case, you want to use family income instead of propensity score because of the practical purpose. Propensity score is not an actual variable. That is a problem. But still, propensity score is of theoretical interest. So you have to understand that we are studying this for theoretical purpose. And another way to still, the propensity score matching estimator is useful as an intermediate goal to obtain the unconditional, the overall average treatment effect, or the average treatment effect on the treated. So in the last class, I have explained the difference in interpretation of these two parameters. So depending on the context, one may be more useful and more relevant than the other. So the propensity score matching estimator can be applied to this idea can be applied to calculate these guys, right? And to do that, as we did last time, we can express these parameters as weighted averages of the propensity score specific treatment effects. Right? Remember, last time we expressed the regression coefficient average treatment effect as weighted averages of matching estimator based on X. We can do the same thing. So, this is like two steps. First, we will calculate the propensity score matching estimator, and then find an appropriate weight to obtain the parameter of interest. So if you want on the average treatment effect, you can calculate the propensity score first, and then estimate the propensity score matching estimator, and then calculate its weighted average. But in fact, there is a theorem that combines these two steps into one. That's the Horowitz-Thompson estimator. What's surprising is This estimator was developed in 1952, even before the Second World War ends, and right? So that is the propensity score. Using the propensity score P, you can write the average treatment effect, overall average treatment effect, not conditional on anything. Overall average treatment effect can be written in this way. So just it's one step. If you estimate the propensity score, then just calculate, you observe D, you observe Y. So calculate, follow this formula and take the average. That's the average treatment effect, which is much easier than the matching estimator. Anyhow, in the end, you don't need the propensity score itself, but you need this parameter. Then this is an easier way to utilize, more efficient way to utilize the same propensity score. This is a very interesting and clever way to estimate the average treatment effect. Furthermore, we may do the similar thing for the average treatment effect on the treated, average treatment effect on the treated, or the regression coefficient in a similar way. That's in general, you may write this as, so remember, so this is just expectation of this guy, but if you put some weights on inside the expectation, then depending on this weight, the parameter can become average treatment effect on the treated or the regression coefficients. So these parameters are just different weighted averages of this estimate, of this Horvitz-Thompson estimator. That's the average treatment effect on the treated is based on this weight, and regression coefficient is based on this weight. So depending on the weight, the parameters may be different, and this is also easy to calculate. You already calculated propensity score, and you observe how many people actually took the treatment. And also you can do this and this, right? By the way, if you compare this weight to the last class, what I did last class, it's pretty much the same. So the numerator is the variance of treatment conditional on X. So if you remember, last time I told you the regression weights are proportional to the variance, and the variance actually equals to the probability of treatment and probability of non-treatment. And as you can see, same form is found here. So idea is the same, but everything is going through the propensity score. So all our analysis, for our analysis, the propensity score is sufficient. That is a very interesting result. Okay. Finally, the third problem of the propensity score matching estimator. Okay. So far, we focused only on the decision-making process, because that's how we check the conditional independence assumption. However, there is actually another dimension, that is the outcome, how to explain the outcome. In other words, so the propensity score is to explain the treatment decision. However, it does not explain the outcome, right? For example, we learned that occupation is a bad control in the college education example, right? So because occupation is a result affected by the education decision. However, also at the same time, we know occupation is an important determinant of wage. So outcome, wage, to explain the outcome, we want to include occupation. So if occupation is available, we don't need to delete that. We have to utilize it somewhere in our analysis. Then how can you do that? Then we so we want to utilize the occupation, but the propensity score does not have any room to include this variable. So here, this is another problem of the propensity score matching. And because of this problem, we want regression again. Regression is almost always the best method to accommodate other variables, right? Easiest way to include more variables. Then put it this way. Earlier, we already learned the problem of using occupation in a regression. That was a problem. But now we can fix the problem using the propensity score. Then we can use occupation in regression. Let me show you how to do that. So here is a real data experiment. We would like to estimate the causal effect of job training program for the unemployed, right? The government subsidized job training like mandatory job training program to get like unemployment benefit. What's interesting here is we have the answer. Actually, we know the answer, but we are not interested in the result of the estimate. But what we want here is we want to compare different methods, and we hope to see which method yields the best, most correct estimate. Okay. So our correct answer is from the national supported work data from 1970s. So this is a randomized experiment on job training program. So from this data, we can easily estimate the effect of job training program because it's like random data, a random controlled experiment. So selection bias is not a problem anymore. But the problem is, now what we are going to do is, we will ignore the data. We know the answer, but for now we pretend as if there was no random experiment. That's actually more common situation. We don't have random experiment data. And then the main problem is, then we have to worry about the selection bias again. And the selection bias arises because those who take part in the training program are not just average workers, right? So we have data, non-random data. In the data, some people take the training, and most of the people actually do not take the training. But these most of people are different from those who take the training. That is the problem. That's the selection. So here, what matters is, usually, those who take the job training program are usually lower earnings potential workers, like low skilled, low educated, people. So the main challenge is in constructing the control group. So we observe a small number of workers who are trained. Then what's their counterpart? We have to match them to a control group. Then what's the control group? That is the main problem if there was no random experiment. This is the common problem in our data analysis. How to find the reasonable control group. And in the in table 3.3.3, 5 different methods are tried and compare which is most correct. For first method is the correct method, randomized control group. We know the answer. So this is the correct answer. So this is our target. We know this is the answer. And in the other 4 methods, we do not use NSW data, but we use current population survey data, which is representative of the whole population in the United States, right? It's a huge data set. Current population CPS data includes like 5% of all the population, things like that. So it's a huge data, but it is not randomized control experiment, right? It includes just everyone. Then, based on the CPS data, we will consider 4 different ways to construct a control group. So how do we compare those who trained to the general population? So the method number 2, the second method uses everyone. And we know it will have selection bias. Everyone in the population is the general population. Then, and as I said, those who participate in the job training program are not average. They are not average workers. They tend to be lower educated and lower skilled. So we expect this method will be biased, will be then different from the first estimate, right? So by comparing the difference, we can see how wrong this is. And the third method is just arbitrary handpicking. I choose younger, less educated, and minor race group and lower earnings guys from the CPS, right? So, it's literally arbitrary. So just you're using your intuition, economic intuition, screen the data to your preference. And number 4 is a systematic and automatic choice of control group based on the propensity score. So in method number 4, you estimate the propensity score first, and then restrict your control group to those who have propensity score between 10% to 90%. So this is possible because actually most of the people will have nearly 0%. For example, like think of me, if I am fired from my job, still I think I'm not going to do the training. So maybe my skill set is cannot be trained in this program. So maybe my propensity score should be 0, right? Given my education and my previous job, my previous income, so I am unlikely to participate in the program. So I should be excluded from the control group, right? That's the meaning of this. So based on the propensity score, the control group is selected. And finally, number 5. First, choose the control group by your own arbitrary criteria, and then utilize the propensity score. So it combines the third and fourth method at the same time. So like in some sense, it refines the control group maybe better using 2 different methods at the same time. So the results are given in there. So think about this. This is the result. Okay. There are 5 methods. NSW is the random experiment result, and number 2, CPS 1 is everyone, not screening at all. And number 3 is handpicked control group. And number 4 is purely automatic selection based on the propensity score. And number 5 combines hand picking and propensity score screening. Okay, and then each rows correspond to the variables used as X. So in the first analysis, demographic controls are used as X, right? So based on this, the truth, here demographic controls, and in the third row, previous earnings in the previous job is used, and demographics again, and more variables. So first, what's interesting here is in the randomized experiment, regardless of the control variables, the estimated results are pretty stable because you don't need conditional independence assumption here. It's already independent. It's already random, so you don't need control variables to guarantee the independence. So here you can assume that the truth is somewhere between 1600 or 1700 something, right? So this is approximately the true value. And now let's think about the second method, no screening. You use everyone as a control group, then the selection bias is huge. As I said, even I am included in the comparison, so I don't believe it. It's totally misleading, right? It's not like, as you can see, if you compare from this one, the bias is minus nearly $10,000. So the bias is nearly 5 times larger than the truth into the other direction. So it's like it's not credible at all. And as you include more variables, it gets better. By the way, everything is based on regression model. So we use regression in the end to estimate the result. And this is regression coefficient using those controls. So anyhow, back to this estimate. So as you include more controls, the selection bias reduced. However, still the bias is huge, right? Nearly, the selection bias is like minus $1,000, which is like less than half of the true parameter. So this method is useless, does not do anything, like nearly useless. And CPS3, the third method is handpicked control group. You choose the control group by yourself according to your own criteria. And then again, selection bias. The selection bias is better than the previous method, but still there are selection biases, but it improves as you include some control variables, and in the end, like pretty close to the truth compared to the previous results. So far, this is the best result. So this tells you that like using whole data is really unreliable. That's useless, but like it is better to like restrict the data using your criteria to match the treatment group, right? So restrict the control group to as similar as possible to the treatment group. That's the interpretation of number 3. And number 4, column number 4. In here we match we construct control group using propensity score screening. And there is big problem here and here. The problem here is, so there is no improvement, nearly no improvement from using whole data. But if you see the final result, it's much better, like nearly as good as your arbitrary method. Okay, then what's the interpretation? So to use the propensity score matching idea, you have to use sufficiently many control variables, right? You have to provide enough information to this algorithm. It's an automatic method. There is no arbitrary method, but you just estimate the propensity score and cut off between 90 and 10%. And then as long as, like, if you provide enough information, it will calculate the estimate in a systematic way, and the result is pretty good. But if the information is not enough, then the conditional independence assumption will not hold, and then you are in trouble. Then it's unreliable in this case. And finally, the final method is to combine both methods, both screening methods. And what's interesting here is, even if you use both, the final result is not as good as the previous ones. So if you want to restrict the control group, you have to choose just one of these two, not using both, because you don't know how your choice is arbitrary, and propensity score is more systematic. They do not go well with each other. So, what you can see from here is, either conclusion, you have to restrict the control group. But of course, I recommend the propensity score screening method, because this is literally arbitrary. So in this example, we restrict the control group to those who have lower education and younger, lower earnings. But how would you do that in another example? So this is an example of job training program. How would you make up a control group in college education or in other hospital example? So it is not a rule. In this example, it worked, but I cannot tell you that this method will always work. So it depends. It's case by case. In some case, it may work well, but in others, it may not. That's the problem. So I cannot recommend this. Instead, the propensity score matching is a systematic and automatic way. So you can apply the same principle to other contexts. Like, it's purely theoretical way to construct the control group. So conclusion. First, in the end, we are going to use regression, but just regression can be wrong. So I recommend to use the propensity score prior to the regression to restrict the sample, to match the sample better. Okay. Many years ago, I used this table as homework, one of the homeworks, but I found that this is very difficult to implement. So I'm not going to do this as a homework. But if you are interested in this data analysis, I have older version of the homework, so I can just share with you in case if you're interested. Okay, this is it, and I'm going to see you. I will see you after the spring break. Okay, bye.